Okay, I am very, very, very sorry for this egregious waste of precious lecture time. Uh, you are to be congratulated. Exam 3 went really, really well. The median score was like 90, which is, I guess I've never seen that before. So, well done. Um, don't be afraid. Please remember that it's not like if you get the grade you earn. So it's not like if the class does really well, I'm wringing my hands in my office wondering what I did wrong and now I need to make the next test harder or anything like that. You're going to get the grade that you earn. You performed well. Good job. If your performance on the exam wasn't what you hoped, let's talk. I will make a video like we've done in the past with explaining the answers to each of the questions. And I think by now you should be able to think after the exam. It makes it so you can see items missed and what your responses are. If it doesn't currently, I'll make sure it does after class. Okay, so we are talking metabolism, and we've been talking about fatty acid beta oxidation. Last time we first activated the carboxylic acid so that we could get a thioester. We first made a mixed phosphoanhydride, and this is AMP, a very good leaving group. And then in the next step, we did a nucleophilic acyl substitution where coenzyme A, thiol, attacked the carbonyl carbon. You get a tetrahedral intermediate, electrons kick down, and the leaving group leaves. And we need CoA here because ultimately we're going to clip off this 2-carbon, carbonyl carbon and alpha carbon to get acetyl-CoA. And as we talked about it last time, the problem with this approach is if we wanted to clip off a 2-carbon unit, breaking a bond between alpha and beta carbons, you'd be thinking, well, what about a retro-aldol or retroclason? But the beta carbon has no oxygen, and you need an oxygen there, either as a ketone for a clason reaction or an alcohol for an aldol reaction. So what we do in the first step is oxidation. We first remove a proton from the alpha carbon to make an enolate. And remember, we said that because thioesters are more reactive than esters, it's easier to make an enolate from a thioester than it is from a regular ester. Once you've made this enolate, we do an elimination reaction using hydride as a leaving group, and we hate hydride as a leaving group except when we have an oxidizing agent nearby. And so this hydride is handed off directly to the electrophilic portion of FAD. We aren't really worrying about why this portion of FAD is electrophilic, only we're seeing that this nitrogen is conjugated to carbonyl oxygens that are withdrawing electron density. You could, by resonance, put a positive charge on that nitrogen. So we're delivering a hydride there and picking up a proton to neutralize the resulting charge. This mechanism is kind of an E1CB mechanism in the sense that it's not concerted. We first remove the proton to get the enolate, and then the hydride leaving group leaves. And the enzyme that does this is called acyl-CoA dehydrogenase. And again, enzymes that are called dehydrogenases catalyze redox reactions. FAD gets reduced to FADH2. Here's the hydrogen we delivered, and here's the proton that we picked up from some other source. Okay, and then we have this alpha-beta unsaturated thioester as our product. Now that's progress because alpha-beta unsaturated molecules are aldol products, so we're getting closer to what we need to have happen. All right, so if you remember, the product of an aldol reaction is a beta-hydroxy. Yes, I know the Apple Pencil battery is low, thank you. The beta-hydroxy carbonyl compound. So now I'm thinking backwards. if I can get an alpha beta unsaturated carbonyl compound from the corresponding beta hydroxy carbonyl compound, then how am I going to get from here the alpha beta unsaturated carbonyl compound to here? What do I need to have happen? Remember what we did in the Aldol reaction? We had a base remove a proton to get an enolate, and then the leaving group, enolate kicked down and leaving group left. What we're going to do now is just exactly the reverse of that. So we're going to take this alpha beta unsaturated thioester, and we're going to do conjugate addition of OH minus to the beta carbon. All right, so here's your thioester with alpha and beta carbons. The enzyme is going to remove a proton from water so that OH minus can attack the beta carbon, and we will break the pi bond and the electrons will go on the alpha carbon. Oops, there we go. Okay, so now we have an oxygen on the beta carbon. And this is why we call this process beta oxidation. Okay, questions about that step? It's just the reverse of the dehydration reaction that happens in the aldol reaction. The enzyme that catalyzes this is called EnolCoA, and this one's fun, hydratase, because we're hydrating that double bond. So sometimes you can get a sense for what the enzyme does based on what the name is. Other times it's confusing. Another confusing thing is sometimes enzymes are named for the reverse reaction, because of course an enzyme doesn't care which direction the reaction goes. All it does is lower the energy of the transition state. So sometimes you'll find enzymes named by the reverse reaction. Okay. So now what we've got is something that looks like an aldol product. Let's think about what we might do if you were to go backwards, or rather, I guess in this case, forwards. What would the aldol starting materials have been here? Go ahead.
Where did the electrons go?
Oh, right, I skipped a proton transfer step. Sorry. They disappeared. So we'll pick up a proton from somewhere, possibly the conjugate acid of the base, and then we get the desired product. Thank you. Thank you for noticing that. I totally forgot that. All right, what else? So if we were to think, okay, what's the retroaldol reaction? We would break this bond. What would the two partners be? Let's deal with the nucleophile. What would the nucleophile have been? What would have had to be on the alpha carbon? It's a retroaldol. Yeah. Would it have been an enolate? Okay, let's see. Well, that is the nucleophile in the aldol reaction. Good. And our reactive partner And sometimes when deciding what the reactive partner could be, when thinking on the retroaldol, it's good to draw in all the substituents on the beta carbon. So what's my other partner, the electrophile, going to be? Sorry, what? Missed it. Somebody was mumbling. Should be aldehyde. And how do you know it's an aldehyde? If you look at that beta carbon, you see it's got a carbon on it and a hydrogen on it. So it has to be an aldehyde. And the reaction, I realize this is kind of confusing because in this process we're doing a retroaldol, and that's the forward direction for this process. But we're thinking about the products of the retroaldol as the starting materials for the aldol. So I'm sorry for the lingo that's a bit confusing there. But do you see how we could make this product above from the retroaldol? Now, I told you our goal was to clip off a unit of acetyl-CoA. So if we do the retroaldol, we do get a unit of acetyl-CoA out. The problem is that we've got this aldehyde here, and we want to be able to cycle through. That is, we want nature's very efficient, and we don't want to have extra enzymes if we don't need them. It would be really nice if we had a thioester here instead of an aldehyde, because then this could go right straight back to step 1, thioester oxidation, without needing a separate type of enzyme. Sorry, yeah, this is the starting material. So by the time we're done, we want the carbonyl carbon of whatever's left in the fatty acid to be a thioester with CoA on it, so that we can just crank through the process. So that the retroaldol is really not our best choice, because once it's done, we've got to somehow deal with this aldehyde. Okay? I'm sorry, I'm thinking, because of my sons, I'm thinking Hamilton. It might be nice to have a thioester instead of an aldehyde. Coming to a theater near you. Everybody's going to want to see that one, I can tell you that. Okay, so instead of trying to do the retroaldol, what we're actually going to do at this stage is we're going to oxidize the beta hydroxythioester, to a beta ketothioester. And remember that beta ketothioesters are Claisen products. So how are we going to do this? Well, here's your beta hydroxythioester. We're going to use NAD+, and I believe I've shown you a mechanism before where we used NAD+. Maybe not. Did we do? Yeah, that was last time. We did. We oxidized glycerol using NAD+. So I'm not going to show that mechanism. You can go to your notes from last time and see this, and we're going to write it the same way that the biochemists do. Understand that basically what's going to happen here is that a base is going to remove this proton, and then this hydride is going to be delivered to NAD+. I told you I wasn't going to show it, and now I'm showing it. So it is pointless to resist. I told Amber the other day that from now on, when I tell her I love you, she should respond, I know. It's a Han Solo, Princess Leia reference, yeah. My sons tell me that jokes aren't funny when you explain them. But, yeah. So, yeah, I actually feel more love if she just says I know than if she says love you too. Okay, so we're removing a proton from our alcohol, and then hydride is being delivered as a leaving group to NADH. And that ends up, oh shoot, got that wrong, sorry. The hydride ends up here. Okay, so now we've got the beta keto thioester, and this is a Claisen product, right? The enzyme that catalyzes this, I don't know what it's called, it's some kind of dehydrogenase. So if this is a Claisen product, what were the starting materials? Recall that the Claisen reaction involves two esters, one of which you make an enolate. Then you attack the carbonyl carbon to get a tetrahedral intermediate. So far this reaction is exactly like the Aldol reaction. The difference here is that you've got something on that tetrahedral carbon that is a decent leaving group relative to a negatively charged oxygen. And so we can kick off the negatively charged oxygen as a leaving group, and we get the beta keto ester. And if we were going to go in the reverse direction, what we would simply show here is the alcohol attacking the carbonyl carbon to get a tetrahedral intermediate. And then, as electrons kick down here, we would show the enolate leaving instead of the other way around. That's the retro-Claisen. Okay? So remembering that our goal is to clip off a unit of acetyl-CoA whilst at the same time having a thioester at this beta carbon, what do you think's going to happen in step 4? What could I do to end up with the following products? What do you think? How's that reaction work? What's my first step? Oh shoot, it's more complicated than I wanted it to be. Oh no, that's right. We love complicated stuff, don't we? Okay. Well, so it's actually known what the enzyme does. We could make this really simple, but sometimes reality is more complicated than we think it needs to be. So the enzyme is called ketoacyl-CoA thiolase instead of hydratase, because we're going to end up having a thiol attack the beta carbon as part of the retro-Aldol reaction. So how does this work? Well, I'm going to just scoot this down because when I copy the notes out as PDF, it doesn't like it when stuff crosses the page boundary. All right, so there's a histidine residue in the enzyme. It's position 375, and here is the structure of the histidine side chain, and I know you guys know that structure because you did so well. So it's lone pairs on that histidine that are going to remove a proton from cysteine 125. Now, that should make you a little bit uncomfortable because you know that the pKa of cysteine is 8, whereas the pKa of the conjugate acid of histidine is 6. So that seems like it shouldn't be really that favorable. Nevertheless, remember, enzyme active sites are not the same as bulk water. pKa's can change, especially in less polar environments. So this works, and if it didn't, we wouldn't be alive. So there we go. What will happen after the cysteine is deprotonated is we're going to use that thiol to attack the carbonyl carbon to get a tetrahedral intermediate. So let's show you the intermediate that we have at this point. Negatively charged carbon, or oxygen, cysteine 125 here, and then the alpha and beta carbons of our thioester there. So electrons on the carbonyl oxygen are going to kick down, and the leaving group leaves as an enolate. As it's leaving, it steals a proton from another histidine residue. Another cysteine residue. This is cysteine 403. Do you have to memorize that? Please, please, please do not. So we've now got an enzyme-bound thioester and acetyl-CoA, which we now send to the citric acid cycle. Now, where does the other portion of our product go, this other thioester? Well, there was a reason we deprotonated that other cysteine, and that's so that it can be a base as the thiol from acetyl-CoA gets deprotonated, and then that thiol attacks the carbonyl carbon. You get a tetrahedral intermediate. This process here is just called thioester exchange, because we're basically going to swap out one thioester for another. Electrons will kick down, cysteine leaves, and on its way out, it's going to steal its proton back, from histidine, whatever on earth it was, 375. I guess I didn't put my arrow in the right place. As that cysteine thiol is leaving, and that gets us back to our enzyme starting state, plus we now have a slightly shorter fatty acid truncated by 2 carbon units. And then we will take this back to fatty acid oxidation, or beta oxidation step 1. And so we will continue to cycle the fatty acid through this process until we have clipped off all of the carbons as acetyl-CoA. So some of you might be asking, what if we have an odd number of carbons? And for the most part, we don't in nature, because the process of making fatty acids starts with acetyl-CoA and basically does this process backwards. So you could imagine starting with a molecule of acetyl-CoA here and negatively charged, make it an enolate, attack here, do the Claisen reaction, and so on backwards. That's how fatty acids are synthesized. We're not going to go through that process because if you've seen it forwards, you've basically seen it in reverse. The enzymatic machinery is a little bit different. But because our fatty acids come from this process, when we break them down, because they come from this process, they have an even number of carbons, so they can be broken down evenly into 2 carbon units. All right, questions? Want to ask about that? Yes?
Does this process change when you have a saturated versus unsaturated fatty acid chain?
It's a good question. Does the process change when it's saturated versus unsaturated? I suppose it depends on where the double bond is. Because if the double bond's in the right place, you can just skip straight to this conjugate addition step without an oxidation. If it's in the wrong place, you might have to reduce it first and then start. So it's a great question. I just don't know. I don't know what the machinery is, but it's one of those options. Okay, what else? All right, so that's lipids. We will talk soon about what the fate of acetyl-CoA is, but let's now talk about carbohydrates. And the process of breaking carbohydrates down is called glycolysis. Dun, dun, dun. So in glycolysis, and this happens in the cytosol, you're going to take 1 molecule of glucose, which is C6H12O6, and 2 molecules of ADP, and you're going to need 2 phosphate groups, so we're abbreviating that with the typical biochemistry notation, plus 2 molecules of NAD+, plus 2 molecules of water. Don't worry about that. That's just about balancing the equations. And we're going to get out of that 2 molecules of something called pyruvate. And pyruvate is C3H4O3. Looks like this. You're going to get 2 molecules of ATP, 2 molecules of NADH, and 2 H3O pluses, which again, we're just sort of balancing things and keeping track of the protons. Okay, so 1 molecule of glucose, 2 of ATP, and 2 of NADH. If you take the NADH to the electron transport chain, every NADH, I think, gives you 2, maybe 3, I'm probably wrong, 2, maybe 3 molecules of ATP. So the process does give you some energy-rich molecules like ATP, and again, we can take NADH to the electron transport chain in mitochondria, but there's still a lot of stuff to be done to pyruvate at the end of this process. So there are a couple of phases of glycolysis, this breakdown process. There's, I think, 8 or 9 different steps. Some of them are the investment phase. We're actually going to consume a couple molecules of ATP just to get started, but we're going to make those back and then some. All right, so the first step of glycolysis is, and we'll call this the investment phase. Fortunately, this is not a Ponzi scheme. We actually are going to get our money back. We're going to take glucose in its cyclic chair form. I'm going to be sort of agnostic about which anomer it is, mostly because I don't know. If the enzyme prefers one versus the other, that's fine. The process here is going to be alcohol phosphorylation, which you saw earlier when we phosphorylated glycerol after hydrolyzing triglyceride. So I won't draw the mechanism for you here since you've seen something similar before, but the product ends up putting a phosphoester on at carbon 6, of glucose. Unsurprisingly, they call this glucose 6-phosphate. And of course, this is just, and frankly, at this point, when people think about glycolysis, they forget about the beta-D-glucopyranose business and just say glucose. That's sort of just implied. The enzyme that catalyzes this is called hexokinase because it phosphorylates a hexose, which is a 6-carbon sugar. And this process is really downhill in energy. It's downhill by negative 8.1 kilocalories per mole, which means it is basically irreversible. Once you start down the dark path, forever will it dominate your destiny. Shoot, the Apple Pencil has run out of juice, so I need to pause our recording. Professional, I would have charged that overnight, but I got to tell a fun story. So, this reaction is essentially irreversible. There is a reason why, and that is because ATP has a phosphoanhydride bond that is less stable than the phosphoester that we're getting at the end. Okay, and I want to make something absolutely clear here. There's this idea that if you break bonds, it releases energy, that you somehow get, I think, from maybe high school, ATP stores energy, and then you break the bonds and energy is released. Yes and no. The only reason energy is released is because the bonds you break are weaker than the bonds you form. So never forget that bond forming releases energy, bond breaking takes energy. We're breaking a less stable bond and replacing it with a more stable bond, and that is downhill in energy. All right. So, dang it, where's the mouse? The next step is an isomerization step. We're going to take glucose 6-phosphate and I'm going to just abbreviate the phosphate group like this. And then we're going to isomerize it to fructose 6-phosphate. And I'm going to try to explain why. This may seem pointless, but it's actually essential to the strategy of the whole process. So give me a second to draw fructose. Fructose is a furanose, that is, it has a 5-membered ring. It is a ketose in the sense that it is a ketone rather than an aldehyde. And I'm going to label the atoms of the ring 5 and 6. 1, 2, 3, 4, 5, and 6. So you can see that we need to move the anomeric carbon over from carbon 1 to carbon 2. It may also be useful to see the open chain forms of these molecules. So we know you can open up the cyclic hemiacetal to get this structure. Okay, and we could similarly open up, shoot, did I do something? I'm sorry, I just want to make sure I didn't do something wrong. Okay, and then we can show the open ring structure of fructose. And so if you compare those two, you can see that we've basically swapped out two groups. You might look at this and say, oh, it's an oxidation reaction because I oxidize this secondary alcohol to a ketone. But then again, it's also a reduction reaction because I reduce this aldehyde to an alcohol. It turns out that you don't need any redox reagents to do this. You simply need the ability to make enolates. Okay? So the process of converting one to the other involves two different tautomerization steps. I will point out, I guess, before we do that, that the enzyme that catalyzes this reaction is called glucose 6-phosphate isomerase. Ooh, because it isomerizes the glucose molecule. The delta G, change in free energy for this reaction, is basically 0. The equilibrium constant is close to 1. There's not a huge energy difference. And this is true for a lot of the steps. It's only a few of the steps that are irreversible. All right, so if you look at what we've got going on here, if we have a base remove the proton that's alpha to the aldehyde, we're going to get an enolate. So here's that enolate, negative charge here. And that, of course, would have a resonance structure that would put the negative charge on the oxygen. But in the next step, we're going to have electrons kick down, and we're going to pick up a proton on, and I'm not sure whether it's from the enzyme or from water, so we'll just be very general there. That's our first tautomerization step. We made an enol from an aldehyde. Okay. So here is the double bond, and there is the OH of our enol. That's a tautomer of the aldehyde because we've moved where the double bond is and we've moved the proton. But the beautiful thing about this enol is it's not just any enol, it's actually an enediol. You could think of this as an enol in the pink direction or an enol in the yellow direction. Do you see that? So when I get to this intermediate, I can choose whether I want this oxygen to be the carbonyl oxygen and this to be the alpha carbon, or whether I want this oxygen to be the carbonyl oxygen and this carbon to be the alpha carbon. Do you see that choice I've got there? If I choose the pink pathway and go backwards and make the enolate and go back, that will take me back to the aldehyde. But if instead I remove a proton from the yellow OH group, that will make a new enolate. That'll make a new enolate, which is resonance stabilized on the oxygen and on this alpha carbon. And then I can have electrons kick down, pick up a proton from some other source on that alpha carbon, and that gets me to fructose. Okay, so it's really simple to take an alpha hydroxyaldehyde and convert it into a alpha hydroxy ketone. You just need 2 tautomerization steps. All right, sorry for the delay at the beginning and the big weird story in the middle. Thanks, have a good day and a fantastic weekend.